Let's take a look at section 3.4, talking about zeros of polynomials. Now, in a previous section, 3.3, we saw that we can use synthetic division to help us factor out a polynomial. But in order to do that, we needed to know one of the zeros of that polynomial. Once we knew one of the zeros, we were able to then use that information to factor the polynomial. So let's take a look at now how we can do that for ourselves, how we can factor the polynomial without being given that information, how we can find it for ourselves. So we're going to begin with what's called the rational zeros test. So the rational zeros test is a way of looking for all of the rational zeros that are for any particular function. Note that they have to be rational, either whole numbers or fractions. If a square root or an imaginary number is a zero, this test won't find them. That being said, most functions that we're going to be looking at will have at least a couple of rational zeros. So the rational zeros theorem states that if you have a polynomial function, let f of x be equal to a sub n x to the power n plus a sub n minus 1 x to the power n minus 1 plus dot 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 plus a sub 1 x to the first power plus a sub 0. Let your polynomial function have this form. Now, the stuff in the middle here, you notice I put dot dot dot. It won't actually matter. We don't care about these terms in the middle. The only ones that will matter will be this very last one and this very first one. Okay? So let f of x equal to this form. If a number, we'll call it z. If z is a zero of f of x, then z must be of the form p over q, where p is a factor of a sub 0 and q is a factor of a sub n. Or in other words, if you have a 0, then it must be true that the numerator of that 0 is a factor of this number back here, and the denominator of that factor must be a factor of this constant up here. Now, that seems a little complicated in its current form, so let's take a look at it with an example, and we'll see that it's not anywhere near as bad as it might look at first. So as an example, let's consider the function, and we're going to go ahead and factor the function f of x is equal to 3x to the fourth minus 2x to the third minus 21x squared minus 4x plus 12. Okay. Notice, unlike in the previous section, we're not saying given that this particular number happens to be a 0. Here we're not given any information. Now notice, if you try to factor that in any way that we've seen in previous courses in high school algebra or in pre-algebra here, it's not accessible. It's not something that can easily be done. Here what we want to do is we want to find a 0 of our function. Because once you can find a 0, that will help you start with the factorization. You say, well, how could I find a 0? It could be any number. Well, that's what the rational zeros test does. It helps you narrow down the possibilities. Any 0 of f must be of the form p over q, where p is a factor of your constant. So factor of the number 12, and the denominator must be a factor of our lead coefficient, in this case the number 3. So it would be over a factor of 3. And you know, there's not too many numbers that are factors of 12, and there's not too many numbers that are factors of 3. So here, when we say any 0 of f must be of this form, we don't have a lot of choices. The factors of 12 are, well, let's see, 1, 2, 3, 4, 6, and 12. Those are all the numbers that could be divided into the number 12. The number 3 has even fewer options. There's only 1 and 3. Those are the only numbers that can be divided into the number 3. So what we want to do is we want to say, let's create P over Q. Let's create a fraction that has one of these numbers as the numerator and one of these numbers as the denominator. Now you say, well, which one? Well, we don't know yet. We're going to create every possible one and then start testing. So let's see here. 1 over 1. Well, that's the number 1. 2 over 1, 3 over 1, 4 over 1, 6 over 1, and 12 over 1. Notice all I'm doing is I'm making fractions with these as my numerators, and I'm using this one as my denominator. Now let me move on. Let me use these as my numerators, and now let me use this one as my denominator. All right, so 1 over 3, and 2 over 3. The next one is 3 over 3. But notice 3 over 3 is the number 1. And we already have the number 1. So I'm not going to write that one again. It's not wrong to write it again. It's just a little bit of a waste of time. 4 over 3. Okay, 4 over 3. 6 over 3 is the number 2. And we already have that. So I'm not going to bother writing that again. And 12 over 3 is the number 4. And we already have that. So these are possible zeros of my function. Now, there is one extra thing we have to worry about here. Because note that if your number can be divided by the number 6, it can also be divided by the number -6. That is to say, every one of these numbers, if the number 12 is divisible by these, it's also divisible by the negatives of these. Likewise, if the number 3 is divisible by these, it's also divisible by the negative of these, which means that my possible zeros aren't just these fractions, but they're also the negatives of these fractions. All right, so we've narrowed it down from we have no idea what our zeros are, we have no idea what our possible answers could be, down to it's got to be one of these 18 numbers, which 18 is kind of a lot, but it's definitely better than we have no idea what we're doing. So now the question is, well, which of those work? It can't be all of them. This is a 4th degree polynomial function, which means that we're going to factor it into, as we've seen in previous sections, it's going to factor into, it looks like 4 different factors, or at least, or rather, it'll factor at most into 4 different factors. That's a lot of numbers, a lot more than 4, so they can't all work. So what we do now is we use synthetic division to test them. I know one of these has to be a zero of my function. In fact, probably several of them, but I don't know which ones. So let me go through and test. I'm going to take my original polynomial function, 3 minus 2, minus 21, minus 4, and 12. And I'm just going to pick one of these numbers and divide synthetically by it. Now you might say, well, which is the right one to pick? Well, that's the thing. We don't know. That's why we're testing them. So here I'm going to pick one at random, and I'm going to say the number 2. All right, so let's give that a try. I'm going to divide synthetically by the number 2. All right, let's drop the number 3. 2 times 3 makes 6. Add these together gives me 4. Okay, 2 times 4 is 8, and if I add those together, that's going to give me negative 13, like that, negative 13. 2 times negative 13 is negative 26, and if I add those together, that's going to give me negative 30, and then 2 times negative 30 is negative 60, and if I add those together, I get negative 48. So notice I have a remainder. What that means is this didn't divide evenly into my original polynomial, which means that this was not an actual zero. So here I have a remainder. This is not 0. And because it's not 0, well, then that means this is not a zero of my function. So that one's wrong. And that's okay, because we know some of these are going to work, so we have to test them until we find one that does. All right, let's pick another number. I'm going to do 3, negative 2, negative 21, negative 4, and 12. And I'm going to divide synthetically by, let's pick a fraction this time, just to see what that looks like. Let's go with a third. Let's do 1/3. So here I've picked this one, and there's no guarantee it's going to work. Let's see what happens. So I'm going to drop my 3. Okay. 1/3 times 3, well, that's 1. And if I add those together, that's going to give me -1. Now if I multiply, -1 times 1/3, that's -1/3. And this doesn't look very good, does it? If I add together -21 with -1/3, that's going to give me -63 over 3, minus another 1 over 3 is -64 over 3. At this point, I think it's probably not going to work out. Here, these are fractions, these are whole numbers, and I'm probably not going to get a number that cancels here. But let me keep going, see what happens. If I multiply these together, I get -64 over 9. All right, -64 times 1 is the numerator, 3 times 3 is my denominator. And if I add those together, that's -36 over 9 minus 64 over 9, that's -100 over 9. Looks like that. And if I take -100 over 9 times 1/3, that gives me -100 over 27, which is definitely not 0. I'm not even going to bother to add those because I know it's not 0. Here, that's not 0. All right. So you can tell that sometimes this takes a bit of time and effort. If you're doing these yourself, you might take a few minutes to actually get one that works. Try not to be discouraged. At this point, you should try to pause the video for a minute and try a few more of them. Use the synthetic division to test a few of these, and once you found one, go ahead and continue on with the video, and we'll see. Even if you did not get the same 0 that I'm going to get, you'll get a 0. All right, so give that a try. Pause and practice. All right, hopefully you found one by now. If not, well then we follow along here. Let's see what we get. So I tried a few of these while we were paused, and I found one that does work. So we do 3, -2, -21, -4, and 12. And if we divide synthetically, it turns out that we were close with the original one. -2 is going to end up working. So let's see here. We drop our 3. That's -2 times 3 is you just dropped that one. So -2 times 3 is -6. Add these together gives us -8. -2 times -8 is +16. And when you add those, you get -5. -5 times -2 is +10. And 10 plus -4 is going to give me 6. And then -2 times 6 is -12. And here I get a remainder of 0. So it turns out that this is one of my zeros. And so, using my factor theorem, I get that x minus this number is one of my factors. This is another one of my factors. So what I have so far is f of x is equal to x plus 2 times 3x squared. Oh, sorry, that should be third power. 3x to the third power minus 8x squared minus 5x plus 6. Just like that. Note that that's just, okay, we found one of our zeros was -2. So x plus 2 must be a factor. That's our x plus 2. And then the remaining coefficients give me my other factor. 3, -8, -5, and 6. 3, -8, -5, and 6. So that's a factorization. But now we can factor a little more. Right here, this is a polynomial function. And you know what? I could do the same thing to it. I could use the rational zeros test to factor this thing. Now, before I do that, I should check. Maybe there's another way to factor it. No, it doesn't look like it. I don't have the sum or difference of cubes. It's not the difference of squares. In fact, it's not a square at all. And factoring by grouping doesn't look like it'll work here. So if there's another way to factor this, it'll be simpler than going through the rational zeros test. But since there isn't, well, we fall back to the rational zeros test. So let's do this again. The zeros of this the zeros of 3x to the third minus 8x squared minus 5x plus 6 must be of the form factor of my constant over the factor of my lead coefficient. Which means, well, there's not a lot of choices there. Factors of 6 are 1, 2, 3, and 6. Factors of 3 are 1 and 3. And of course, plus and minus all of those. It's possible that's the positive or the negative factor. So here, we can create all the fractions that we can out of this. We can do 1 over 1, 2 over 1, 3 over 1, and 6 over 1. We can do 1 over 3. We can do 2 over 3. We can do 3 over 3. Yeah, we already have 3 over 3. That's 1. And we can do 6 over 3, which is the number 2. We already have that one. And don't forget that if these numbers are possible zeros, so are their negatives. All right, so we're going to go ahead and give that a try. We have, let's see, what is that, 6? We have 12 possible zeros of this. So we're going to go ahead and pick and continue on trying. So we're going to take this polynomial, and we're going to divide synthetically by these to see which ones work. I'm going to take 3 minus 8 minus 5 and positive 6, and we're going to divide synthetically by, and again, you should pause the video and give this a try. Pick one of these 12 different factors and try it out and see if you can make one work. If you're really trying to practice this, you might even try using one of the fractions and see what happens if you use one of the fractions. All right, so while we were paused, I went ahead and tried a few of them, and I went ahead and did what I said, and I tried a few of the fractions, and it turns out one of the fractions does work out. The number 2/3 works out pretty good. So let's give that a try here. If I use 2/3, which is one of my possible zeros, I'm going to get, I'm going to drop my 3. 2/3 times 3 is 2. If I add these together, I get negative 6. Now, 2/3 times negative 6, that's negative 4. And if I add those together, I get negative 9. And now if I take 2/3 times negative 9, I end up with a negative 6. And if I add those together, sure enough, that gives me 0. So that means that this must be a 0 of one of my polynomial here. So now f of x is equal to, x plus 2 was already a factor. I'm not going to change that. I'm going to leave that alone as x plus 2. But now this one right here, this cubic polynomial, I know that 2 over 3 is a 0 of that, which means that x minus 2 over 3 is a factor of that cubic. The other factor must be what I get once I divide out by x minus 2/3, which is going to be 3x squared minus 6x minus 9, just like that. And now here, this is a quadratic, and I can factor this. Now, at this point, I could do this again. I could use the rational zeros test. Once you get down to a quadratic, though, you probably don't want to, because one thing you've noticed by now is that the rational zeros test is reliable. It'll get you an answer, but it's also kind of long. You got to try a bunch of combinations. Quadratics can be factored a bunch of other ways, which mean that you probably don't have to go through this. Once this is a quadratic, you're probably better off factoring in the traditional way. Notice right here that all three of these numbers can be divided by the number 3. So let's factor out the number 3. When I factor out the number 3, I'm going to put it all the way in the front, just because that's where I usually put constant factors. I'm leaving that alone. I'm leaving that alone. And since I factored out the number 3, each of these gets divided by 3 to give me x squared minus 2x minus 3. And now that can factor out nice and quick, because now that's f of x equals 3 times x plus 2 times x minus 2/3. The two numbers that multiply to give me negative 3 and add up to give me negative 2. The two numbers that multiply to give me negative 3 and that add up to give me negative 2. That's going to be negative 3 and positive 1. So here, x squared minus 2x minus 3 will factor as x minus 3. because of that number, and x plus 1 because of that number. And you note that we have now completely factored our polynomial function. All of these are as simplified as possible, and nothing else will factor out any further. So this all seems well and good, but there is a bit of an issue here. How do we know this is going to work? And we said, well, our rational zeros test, our rational zeros theorem said whatever rational zeros we have, they have to fit this form. Well, yeah, but who said that there's going to be any zeros? Maybe there's a polynomial function that doesn't have any zeros, in which case I'm just wasting my time doing this. Well, turns out that that can't happen. We have a theorem. In fact, this is the central theorem to algebra. It's called the fundamental theorem of algebra. The fundamental theorem of algebra is something that's very simple to state. In fact, it's a two-sentence thing, but it is something very complicated to prove. So we're not going to prove it here. That's something that's left for more advanced classes. Here, we're simply going to state it, talk about what it means, and show how it implies that our techniques not only will work, but that they have to work. So the fundamental theorem of algebra says, let f of x be a polynomial function of degree n, which is greater than or equal to 1. All that means is we don't want a polynomial function of degree 0. We don't want f of x equals to the number 5. We need to have at least x with a power of 1. Right? The reason for that is because a constant, if your degree is 0, then you'd have something like f of x equals 5 or f of x equals 12. It's a number, a constant. And that is not really a polynomial function. It's a constant function. So that behaves a different way. So here what we're saying is let f of x be a polynomial function of degree n greater than or equal to 1. You just need at least 1 power of x. More is fine too. And it should have complex coefficients. Most of the problems that we see in this section and in this chapter will have actually real coefficients, but complex coefficients are allowed as well. And remember, a real coefficient can be thought of as a complex coefficient with its imaginary component set equal to 0. So even though it says complex coefficients, real coefficients work the same way. So if you have a polynomial function that meets all of that criteria, then you can be guaranteed that f of x has at least one complex 0. Let me write that as a word, complex 0. That doesn't sound like a lot, right? It just says there is a 0. It doesn't say anything about how to find it. It doesn't tell you anything about how many there could be. It says there's just at least one. But see, that's all you really need. Because looking back at our previous problem, look what happened. We started off with something that was of degree 4. Well, we found a factor, and we factored it out. Okay, so once we factored that out, that was a linear factor. But then once we factored it out, what was left was now power 3. So we started with something that was power 4, and then we factored out one factor, which gave us something that only had a power of 3. But guess what? This is also a polynomial factor, which means that the fundamental theorem still applies. So I can still find a 0 of this. Okay, so that means I'm not going to waste my time by doing this. I can keep searching to find another 0, and eventually I do. Okay, but now I have, that's my first factor, that's the second factor, and now I have a quadratic. Oh, well, that's also a polynomial function, which means that the fundamental theorem applies here. Notice that all the fundamental theorem does is it tells you every polynomial function has a 0. But if it has a 0, that means that you can divide out by a factor. So what that means is if you have something that's already linear, well, that's 0, right? Negative 2 is the 0 of this, and 2/3 is the 0 of that. But this, you can find another 0 that can come out of this, and so you can find another factor that comes out of this. So here, this quadratic can factor into a pair of factors. And so what happened was you started with something that was power 4. Now you have linear times power 3. And now you have two linears times power 2. And in the end, you end up with 1, 2, 3, 4 linear factors. And a constant, which doesn't give you any zeros. We can summarize all of that with another theorem. This is called the linear factorization theorem. The linear factorization theorem says, let f of x be a polynomial function. A sub n is the lead coefficient. That's going to be important here in a second. The degree of the polynomial function should be greater than or equal to 1. So again, just don't have any constants. Don't have any constant functions. And here the lead coefficient should not be 0. Some number, positive, negative, fraction, whole number, decimal, it doesn't matter as long as it's not 0. If you have a polynomial function with lead coefficient a sub n, and its degree is greater than or equal to 1, then f of x factors into that same lead coefficient times n linear factors. Notice there's the first one, there's the second one, dot, 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 all the way up to n, where this n is the same as the power of our coefficient, of our lead term. Here, z1, z2, all the way up to zn are the zeros of our function and are not necessarily unique. Remember, we can have factors that repeat. We call that having multiplicity 2, multiplicity 3, multiplicity 4, and so on. So it's possible that some of these are repeating, but there are exactly n of them, even if some of them do repeat. You can see that in the results of our previous problem, where, once again, we started off with a polynomial function, 3x to the power 4 plus some stuff. So in the end, we expect this to factor into 3 times 4 linear factors. And that's exactly what we get. 3 times 1, 2, 3, 4 linear factors. These numbers inside of each linear factor represent the zeros of our polynomial function. Since there are 1, 2, 3, 4 of them, which matches to the power 4 of our original problem, then that leads us to our to another theorem. And that is the number of zeros of a polynomial function. Let f of x be a polynomial function of degree n greater than or equal to 1. All right, that's all that matters. We don't care what the polynomial function looks like as long as it's a polynomial and it has a degree that's greater than or equal to 1. If that's the case, then f of x has exactly n zeros, including multiplicities. So it's possible that you only have the number 5 as a 0, but it occurs multiple times. All right? So here, the degree of the polynomial function tells you the number of zeros, including the multiplicities of those zeros. Now at this point, you might say, well, no, that's a lie. Because I can think of a counterexample. I can think of an example where this is not true. So consider the example that looks like this. Now, this is not really a counterexample. The theorem is true, but this helps to show us a little bit more about it. It looks like our theorem is not true, at least at first with this problem. So let's say we're going to go ahead and factor, and let's use something that fits a form, the form of the difference of cubes. So x to the third minus 8, for example. Okay. Now, whenever you have the difference of cubes, that factors as, if you have a to the third minus b to the third, that's going to factor as a minus b times a squared plus plus ab, not 2ab, plus ab plus b squared. All right. So here, that's what we have. In our case, we have x to the power 3 minus 2 to the power 3, because after all, 2 to the power 3 is 8. And so now all we would do is we would plug those numbers in here. So anywhere we see an a, we're going to put an x, and there goes an x, and there goes an x. And anywhere we see a b, we're going to plug in a 2, so there goes a 2, and a 2, and a 2. And I can go ahead and clean that up a little bit. I can write that as x minus 2, and I can write that as x squared plus 2x plus 4. Okay? So now this is factored as x minus 2 times x squared plus 2x plus 4. Just like that. All right, so far so good. That we didn't need any of the rational zeros tests, although if we wanted to, we could have. All right, we have, that's our constant, that's our lead coefficient, and what we would want zeros that were made up of factors of 8 over factors of the number 1. In fact, let's go ahead and write that out. The zeros, now we don't need to do that, we already have the factorization. But let's say we didn't know this formula. We could still use the rational zeros test to do that one. We could say the zeros of x to the third minus 8 must be of the form factors of the constant, which for us is negative 8, and over a factor of the lead coefficient, which in this problem is just the number 1. So here we would have, well, let's see, factors of 8 are going to be 1, 2, 4, and 8. And of course, that's plus or minus all of those over the number 1. So every possible rational zero for this function would be 1, or 2, or 4, or 8. 1, 2, 4, 8. And of course, the negative of those. Negative 1, negative 2, negative 4, and negative 8. And you notice that, well, it turns out that 2 is a zero of our function. So if we didn't know this formula here at all, and we just used the rational zeros test, we would test among these 8 different factors, and once we test all of them, or once we test enough of them, we would eventually find that 2 works out. And so since 2 works out, x minus 2 would be our factor. So even if you don't know this, the rational zeros test will still get you this factorization. But now, if I try to factor this thing, notice that I can't, at least not in the traditional sense, because what I would be looking for are 2 numbers that multiply to give me 4 and add up to give me 2. And there aren't any. There are no numbers that multiply to give me 4 and add up to give me 2. Well, that's not true, though. There are no real numbers that add up to give me 4 and multiply to give me negative 2. Remember, this is a quadratic, which means that its zeros can be complex. After all, the zeros of this come from the quadratic formula. And because the quadratic formula has a square root inside, if that radicand is negative, then that means that the zeros have the square root of a negative inside. Or in other words, we end up with a complex number. So here we can factor this one, not through the rational zeros test, and not through a traditional factoring technique, but rather through the quadratic formula. So let's go ahead and give that a try. Here I can say, okay, the quadratic formula tells me that the zeros of x squared plus 2x plus 4, well, let's see, the zeros of those are going to be negative b plus or minus the square root of b squared minus 4, a is 1, and c is 4, all divided by double the value of a, double the value of 1. All right, negative b plus or minus the square root of b squared minus 4ac all over 2a. We can simplify that. That's a negative 2 on top. That's a positive 2 on the bottom. And now inside of our square root, 2 squared is 4, minus 4 times 1 is 4, times another 4 is 16. And here, 4 minus 16, that's going to give us negative 12. Notice that we're taking the square root of a negative number. Well, that's going to cause an imaginary solution. So here, that's going to give me negative 2 plus or minus. If I take the square root of a negative 12, that's going to be the same as I times root 12. So that's why our rational zeros test wouldn't work here, and that's why our traditional factoring technique wouldn't work here, because neither of those allow you to get complex numbers, but the quadratic formula does. And since we can use that quadratic formula on this quadratic, we don't need to worry about the fact that these are limited to only real zeros. We can still find them, albeit through this path. Here, let's clean that up a little bit more. I can factor out 12 as 4 times 3. And even though I don't know the square root of 4, I know the square root of, even though I don't know the square root of 3, I know the square root of 4. So if I write the square root of 12 as the square root of 4 times 3, That's the same as the square root of 4 times the square root of 3, which is 2, and then the square root of 3, well, I have to leave that alone. So that's going to be plus or minus, instead of saying I times root 12, I can say I times 2 root 3. Like that. And all of that's being divided by 2. And finally, I can divide each of these by 2. So that'll give me negative 2 over 2 is negative 1, plus or minus. Here, these two divide away, giving me I root 3. Notice these are two separate zeros. They are two different answers, negative 1 plus I root 3 and negative 1 minus I root 3. So coming up over here, if these are the zeros of my quadratic, then x minus these numbers gives me the factors of my quadratic. So coming up over here, I can write this as x minus 2. I just bring that down. And now x squared plus 2x plus 4 factors as x minus something and x minus something else, where those two somethings are these two zeros that we just found. So up here, I can write that as x minus, I'll use this zero here first, minus 1 plus I root 3. And then I'll use this 0 over here, and I'll write that as x minus negative 1 minus I root 3. You can distribute that negative throughout, and that's going to give you x minus 2. I'll leave that alone. And now if this negative distributes there and there, double negative makes that a plus, negative of a positive makes that a negative, so we get x plus 1 minus I root 3. I just distribute my negative there and there. And same thing here, this negative makes both of these positives. So that's going to give me x plus 1 plus I root 3. And there we go. Our number of zeros of our polynomial function still holds true because we had a polynomial function of degree n greater than 1, and we had exactly n zeros. Here we had a polynomial of degree 3, and it factored out into exactly 3 factors, which means we had exactly 3 zeros. No one ever said they had to be real numbers. Complex numbers are perfectly acceptable as zeros. There is one other thing to notice about this example, and that's that these two zeros are almost exactly the same. Negative 1 plus I root 3 and negative 1 minus I root 3. And you say, well, sure, they came from the quadratic formula. The quadratic formula gives me two answers that are the same, except one's a plus and one's a minus. What that brings us to is another theorem, though. Because anytime we have a complex solution, if you notice, these multiply back out to give me this. If I only had one of these as a complex 0, multiplying this out would give me a complex set of numbers. Here, I don't have a complex set of numbers, which means that anytime you have a 0 that is complex, if you're expecting it to work out to give you nice, pretty whole numbers or fractions without any complex numbers in your polynomial, that means that you had another complex number that, when combined with this one, canceled out all the nastiness. In other words, you have its conjugate. So that brings us to our fourth theorem for the section, and that's called the conjugate zeros theorem. The conjugate zeros theorem formally states what I just babbled on about. Yeah? The conjugate zeros theorem says let f of x be a polynomial function with real coefficients. They don't have to be whole numbers, but they do have to be real, something with without anything that's complex. Now, if f of a plus ib is equal to 0, for b not equal to 0, here you don't want this to be disappearing on you. You want this to actually be complex. If you have a complex number that's a 0, then the conjugate is also a 0. If a plus ib is a 0, a minus ib is also a 0. So let's take a look at an example of a problem like that. So let's try this here. Our question is to factor the function f of x equals x to the fourth minus 6x to the third plus 5x squared plus 30x minus 50. And here we're given a 0, but unlike in previous examples, here our given 0 is a complex number. All right? So just like with the real zeros, they give us a factor. So this tells me that x minus 3 minus I is a factor. And that just comes from the factor theorem. If I have a 0, x minus that 0 gives me a factor. But now, by using the conjugate zeros theorem, the one we just stated, the conjugate zeros theorem says, well, if that's a 0, then I can automatically assume that its conjugate is a 0. So f of 3 plus I. Remember how conjugates work? They have the same numbers in the same order, but the sign in the middle is going to change. So 3 minus I is now 3 plus I. That's also going to be a 0. So this is from our factor theorem. And this is our conjugate zeros theorem. But now, because we have a 0, we can use the factor theorem again to tell us that x minus that 0, x minus the number 3 plus I, is a factor. And again, that's our factor theorem. So notice we already have two factors. This is a fourth degree polynomial, which means we know we're going to end up with 4 factors. We already have 2, so we can just find the other 2. How do we do that? Well, it might be what you're afraid of. We're going to be using synthetic division. At this point you say, well, we're using synthetic division, but our zeros are complex. Well, that's right. No one ever said that the numbers in synthetic division had to be real or imaginary or complex or anything else. They just have to be numbers that are the coefficients and zeros of a polynomial function. So here, it may look a little strange, but we're going to do synthetic division using these imaginary numbers. So let's give this a try. Here's my polynomial function. So as with any synthetic division, let me start by writing down the coefficients in order. I'm going to have 1, negative 6, 5, 30, and negative 50. And then I'm going to divide synthetically by one of my zeros. I have 2 of them. I'm going to just pick one. I'm going to go ahead and pick 3 plus I. Just pick one of these 2. It doesn't matter which one. We're going to be dividing by both of them eventually. So we just got to pick one, and once we're done with that one, we'll do the other. One thing that you'll notice about dividing synthetically by complex zeros, since we're going to be using the conjugates, the pattern will always be the same. The first division will be long and somewhat complicated. The second division will be very short and very quick. If it doesn't look like that, if the second one isn't short and quick, there's probably something wrong. So let's see how this looks. The pattern of synthetic division has not changed in spite of the fact that we now have a strange looking number here. You're going to take your 1, you're going to drop it straight down. That's a 1. And now we're going to multiply. 3 plus I times 1, well, that's 3 plus I. And now if we add those, when you add complex numbers, real with real, imaginary with imaginary, negative 6 plus 3 is negative 3, and the I is just going to stay an I, right? Because there's no imaginary number for it to combine with. So now I'm going to multiply 3 plus I times negative 3 plus I. 3 plus I times negative 3 plus I. And when I multiply complex numbers, I do that by distributing. So 3 times negative 3 is negative 9. 3 times I is 3i. Negative 3 times I is negative 3i. And I times I is I squared, like that. Here I notice 3i minus 3i is 0, so that's gone. And I remember that by definition, I squared is equal to negative 1. So really this is negative 9, and plus I squared, that's the same as saying plus negative 1. And so that's going to give me negative 10. So that's the number that goes here. That's negative 10. So now I add those, and that's not too bad. That's just a whole number. That's going to be negative 5. And now we're going to multiply 3 plus I times negative 5. And remember, when you're multiplying complex numbers, it's done by distributing. So negative 5 times 3 plus I, well, that's negative 15, and that's negative 5i. Negative 15 and negative 5i. If we add these, 30 plus negative 15, well, that's 15. And here, negative 5i has no imaginary number to combine with, so it stays negative 5i. And finally, we're going to multiply these together. And we're going to take 3 plus I times 15 minus 5i. 3 times 15 is 45. 3 times negative 5i is negative 15i. I times 15 is 15i. Negative 5i times another I is negative 5i squared. These two subtract away. 15i minus 15i, that's gone. And remember, I squared is the same as saying negative 1. So negative 5 times I squared is really negative 5 times negative 1, which is positive 5. So here that's going to be 45. These are gone. And that's now positive 5. And if I add those together, I get 50. So here, 3 plus I times 15 minus 5i is the number 50. And if we add these together, we get no remainder. So that's a good indicator, right? We divided correctly. Here, when we plug in x is equal to 3 plus I, we're supposed to get 0. Okay, so that's a good indicator that we divided correctly. This can take a bit of effort, so that's a nice indicator. If this isn't 0, then something went wrong somewhere. Now, we've divided synthetically by one of our zeros. We've used this one already. So now let's go ahead and use the other one. Let's go ahead and divide synthetically by 3 minus I. Here, we can just continue on down the line because these are the coefficients of our new polynomial. So we can just continue dividing from here. The remainder is gone. There is no remainder, so we don't worry about that. So this is the remaining polynomial. 1x to the third minus 3 plus ix squared minus 5x plus 15 minus 5i. And since those are already the coefficients, we're not going to bother rewriting that as a polynomial. Let's just continue with our division. So I can now divide by 3 minus I. Notice I'm using the other one here. And you'll notice that this one will work out much more simply than the previous division. It's always going to work that way. If I take the 1 and drop it, that's the number 1. 1 times 3 minus I is 3 minus I. And when I add those, well, look, stuff cancels out. 3 and negative 3 is 0. I and negative I is also 0. So that whole thing is 0. And something times 0 is going to stay 0. When I add those, I'm going to get negative 5. And then if I multiply these, well, let's see. That's going to be 3 minus I times our negative 5. And that's just going to distribute. Negative 5 times 3 is negative 15. Negative 5 times negative I is positive 5i. And so negative 15 plus 5i. Notice that's 0 and that's 0, which is what we were expecting. We were expecting the result to be 0 because we know that 3 minus I is a 0 of our factor. We were given that. But now we have our polynomial function factored out significantly. So let's take a look at what we have so far. Our polynomial function is f of x equals x to the fourth minus 6x to the third. I'm just rewriting the problem right now. Plus 5x squared plus 30x minus 50. And using our synthetic division, we found that we know x minus 3 minus I and x minus 3 plus I are factors. So let's write those down. X minus 3 minus I and x minus 3 plus I. But once we divided synthetically by each of those, we had another polynomial, no remainder. That's a constant. Notice there is no first power, so we don't worry about that one. And that is second power. So x squared, no x, minus 5. X squared minus 5. Just like that. Here, we can go ahead and distribute that negative. So I can write that as x minus 3 plus I. And here if I distribute that negative, I can write that as x minus 3 minus I. And that's x squared minus 5. Notice we're almost done. We started with a polynomial function of degree 4. We now have 3 factors. This one's not linear yet, and our linear factorization theorem says we're supposed to get 4 linear factors. Those are already playing along. This is still not linear. So we can factor this one a little bit more, and we can do that by finding its zeros. Here we can find the zeros of that one by just extracting the square. So the zeros of x squared minus 5. Well, we can take x squared minus 5 and set that equal to 0. If we add 5 to both sides, we get x squared equals to 5. And now I can take the square root of both sides. Now remember, there are 2 different roots, so that's going to be plus or minus the square root of 5, which does give me 2 separate answers. I get x is equal to root 5, and x is equal to negative root 5. That's what plus or minus means. There's 2 of them. They look the same, but with opposite signs. So if those are the zeros of this factor, then x minus these numbers must be the factors of x squared minus 5. So to wrap this up, we get x minus 3 plus I times x minus 3 minus I. Just brought those straight down. And now x squared minus 5 factors is x minus something and x minus something else. And those 2 somethings are these numbers here. So this would be x minus root 5 and x minus a negative root 5. And minus a minus would be plus. So I can write that as x plus root 5. And there we go. Notice that the rational zeros test would not have worked for this problem at all because none of these zeros are rational numbers. Square roots are irrational numbers, and these are complex numbers. So we do note that there are a few things about polynomial functions that we can't quite do yet without the rational zeros test. This could not be factored if we hadn't given you that very first zero. So there are a few things about polynomial functions that we don't really get to in this class. The rational zeros test combined with the factor theorem combined with the complex zeros theorem is going to give, the conjugate zeros theorem, is going to give you everything that you need to factor any polynomial you see in this class. That being said, keep in mind that there are some more advanced topics. For example, one might ask, well, if the rational zeros test didn't work here, then how did you get that number? How did you get f of 3 minus I is equal to 0? Well, again, there's some things that we can't do in this class, and those are best left for more advanced classes. But any polynomial function that you see now, if you combine the rational zeros test, the fundamental theorem of algebra, the linear factorization theorem, and the conjugate zeros theorem, that will be sufficient for you to factor anything and everything that you can see here. For our last problems, let's take a look at something that asks us to take a function and build it. In other words, we're going to go backwards from what we usually do. Usually we're told, here's a built polynomial function, go ahead and break it apart. Now they're going to give us a description of the polynomial function and ask us to recreate it. So let's see here. Let's write a polynomial function. Of degree 3 that has integer coefficients and negative 4i and 3/2 as zeros. Okay? So now, we're going to write a polynomial function of degree 3. Well, that's the easy part, because I know how to count. A polynomial function of degree 3 has to have 3 linear factors. We know that from the linear factorization theorem. So here, that's going to be x minus something times x minus something times x minus something. So now I just have to figure out what those three somethings are. Now here I know that 3/2 is a 0 of my function. Okay, awesome. That means 3/2 must be one of the numbers that goes in here. Because from our factor theorem, we know that if 3/2 is a 0, then x minus 3/2 must be a factor. We're also told that negative 4i is a 0. Okay, so then x minus negative 4i must also be a factor. But now what about this one? Well, note, it says that we have integer coefficients. That's where our conjugate zeros theorem comes in. All right? Here, the conjugate zeros theorem says if you have a polynomial function with real coefficients, and integers are real numbers, then if you have a complex zero, its conjugate must also be a 0. So, by the conjugate zeros theorem, if negative 4i is a 0, you can think of negative 4i as being 0 minus 4i. Then by the conjugate zeros theorem, we know that 0 plus 4i, or we can just say 4i, is also a 0. And that's from our conjugate zeros theorem. So we know that negative 4i is a 0, but by the conjugate zeros theorem, positive 4i is a 0. So that's going to be minus positive 4i, like that. And so now, double negative makes that a positive. So we can write this as f of x equals x minus 3/2 times x. Double negative makes that a plus. So that's going to be plus 4i. And then here, that's x minus 4i, which we can write as x minus 4i, like that. At this point, you could now multiply it out, and I believe in the textbook it even asks you to do that. If you look in the back of the book and look at the answers, it'll have it all multiplied out. I'm not going to require you to do that. These problems are long enough as it is. If you can get this far, I am very, very happy with your ability to handle polynomial functions. Okay. So let's see. Another example. This one has a little bit more information. This one says we're going to find a polynomial function of lowest degree. That has zeros 5, let's see here, with 5 as a 0 of multiplicity 2, negative 3 is a 0 of multiplicity 2, and this is a strange one at first, we want to find that f of 0 is equal to negative 450. Or in other words, we're looking for the y-intercept of its graph to be 0, negative 450. That sounds a little strange at first, and you might think, how am I going to make that happen? But it turns out to be something simple at the end of the problem. Let's start off by building the main part of the problem, the main part of our function, and that's to create our polynomial factors. Now, notice it says a polynomial function of lowest degree. It doesn't tell you what degree it has, unlike the previous one, but all it's saying is don't put in any factors that you don't need. All right? Satisfy these conditions, and then don't put in any more factors that you don't need. 5 is a 0. Okay, well then that means x minus 5 must be a factor. Oh, but it's a 0 of multiplicity 2. Okay, so that's got a power of 2. We also know that negative 3 is a 0. Okay, so then x plus 3 must be a factor. If negative 3 is a 0, x plus 3 must be a factor. And it also has a multiplicity of 2. So that's a power of 2. Okay, so there we go. But now think back to our linear factorization theorem. Our linear factorization theorem says that if you have a polynomial function of degree n, it'll factor into exactly n linear factors and a constant. Now, a lot of times that constant can be the number 1. For example, here, you can imagine this as being 1 times all of this stuff. But it doesn't have to be the number 1. It can be something else. So right here, we're saying if we plug in 0 into our function, we're supposed to get negative 450. Well, let's see what we actually do get. If I try to plug in f of 0, well, let's see, that's going to be 0 minus 5. Well, that's negative 5 squared. And 0 plus 3, well, that's going to be 3, and that's also going to be squared. And that's going to give us, well, let's see, negative 5 squared is positive 25. And 3 squared, 3 times 3 is 9. And if I multiply 25 times 9, I get 225. Well, notice that's wrong, because I wasn't supposed to get negative 225. I wasn't supposed to get positive 225. I was supposed to get negative 450. Well, yeah, but notice that this is just half of that one. Oh, and it needs an extra negative. Oh, well, that's fine. If I were to multiply this by negative 2, then it would give me exactly what I wanted. That would be negative 450, the way it's supposed to be. Okay, well, if I'm multiplying this by negative 2 to make it what it's supposed to be, that means that this was also being multiplied by negative 2. Oh, that means that this was also being multiplied by negative 2, right? This times this is negative 450. But these came from these factors. So if this is getting multiplied by negative 2, that means these factors also need to be multiplied by negative 2. Notice we don't have any new variables, which means our zeros have not changed. We still have 5 as a 0 of multiplicity 2 because of that factor, and negative 3 as a 0 of multiplicity 2 because of that factor. This doesn't have any variables, so it doesn't change the zeros or their multiplicities. But what it does is it corrects this number so that we get f of 0 to be the number that we wanted. So here, the coefficient that is usually 1 for many of our problems, note it doesn't have to be the number 1. Here, by multiplying this times negative 2, that gives us our function, and that gives us our result. At this point, if you want, you can multiply that out. In the back of the book, if you're comparing your answers to theirs, it'll also have it multiplied out. But as I said, if you can get this far and you understand this, I am very satisfied with your ability to handle polynomial functions. So that's it for the section 3.4. At this point, I recommend you go and do the homework for this section. This is kind of a long section with a lot of theorems and a lot of stuff going on. Even though they're all connected, there is a bit of a difference between each of our 4 theorems that we've seen, and as well as the rational zeros theorem that we've added on top of that. So you should go and attempt your homework, because if you wait a while and look at a few more sections, it will confound all the different things that you're looking at. So you want to go ahead and practice this now. Remember, if you have any questions, please feel free to post on the discussion section in Canvas or visit my virtual office hours. And I hope you all have a nice day.